How many different isosceles triangles have integer side lengths and perimeter 23? So to first start this problem, we'll talk about an isosceles triangle. And we know that an isosceles triangle has two sides that are the same length, and in this case we'll call it A, and one side length that is different, which is B. So the total perimeter that we are given is 23. So the perimeter of a triangle is the sum of all three sides, so we know that it's 2A plus B equals 23. Now it says how many different isosceles triangles have side lengths and perimeter 23. So if we go through each possibility for A, we can see which of them B makes sense. So if A is 1, then it would have to be 21, because since the perimeter was 23, we are subtracting 2 times 1. Since 1, we let be A, which is the side length. So we have two sides, so equals 21. So B has to be 21. But this doesn't work because if we draw the triangle out with A as 1, we have a very small side A, and we also have a very large side B, and this does not form a triangle. So 1 as A does not work. If we have A as 2, then B would have to be 19, since 23 minus 2 times 1, 19. This also doesn't work, since we would have two short side lengths and another long third side, and this is not a triangle. So if we go through all the possibilities, we're going to see that A can be 7, 9, 10, or 11. And then we get the B values that make sense for this triangle by repeating the process. So when A is 7, then B would have to be 9, because 23 minus 7 times 2 is 9. And then this would make a 7, 7, 9 triangle. So this would work since we have 7, 7, and a 9 right here. So these two, the sum of these two, the shorter side lengths is 14, and the sum of the two shorter side lengths has to be greater than the third side. And that's called the triangle inequality theorem. And then for next, if A is 9, then B would have to be 5, using the same calculations we did over here. And the triangle for this would be a 9, 9, 5 triangle. The third one, A is 10, B would be 3. We would have a 10, 10, 3 triangle. And lastly, we have A as 11, B as 1, and we would have a 11, 11, 1 triangle. And then we can switch the values for the A. Doesn't have to be the longer side, so we can switch and make A the single different side and B the two equal sides, so we get two more possibilities. So 1, 2, 3, 4. So for the fifth possibility, we can get A to be 9, A to be 9, and then B would be 5. And then the triangle for this is going to be 9, 5, 5. So if we draw that out, then we get 5, 5, 9. So that would make a triangle, so that works. For the last one, we can switch A to be 3, B would be 10. This would make a triangle 3, 10, 10. So if we draw that out, we assume that these are 10s. Let's make it more accurate. So these are 10s, and that is a 3, so it makes a triangle. And then we should note that we can't switch A and B for all of the options we have over here, because if we do that, we might result in some invalid triangles or create duplicates of the triangles that we have already counted. So for example, if A was 7 and B was 9, and if we were to switch this order from 7, 7, 9 to 997. This would essentially be the same triangle as this one, and it would just have the different labels for the sides, so we wouldn't want to count it again as a different triangle. And if we consider this one over here, number 4, where A is 11 and B is 1, if we switch B and A, so we have A is 1 and B as 11, then this would violate the triangle inequality theorem because the two shorter sides, which we have 1 over here, so 1 plus 1, the two shorter sides is 2. So 2 is not greater than 11. So that violates the triangle inequality theorem because if we had 1, 1, and the third side equals 11, this would not be a triangle. So we have a total of 1, 2, 3, 4, 5, 6 options at work, so C is our answer.